Okay, so here we are doing Unit 3, Transformations and Rigid Motions. We are at the very beginning of the unit. This is day 1. I know it would be lovely if I was there in person, but sometimes life just happens that way, and you can move forward without me there and still learn. Amazing, right? Of course it is. So you have your packet, hopefully you were given your packet. These are the 3 standards that we're going to be focusing on with a lot of subparts to that. Here's our lesson plan and our days. So if you're missing a day, you know what's happening on that day that you will be out. We will end this unit right before Halloween. So this will take us right up to Halloween. So what we're going to be talking about for today's lesson is different types of symmetry. And symmetry in our everyday world is all around us, from the rectangles and squares that are used for construction to the emblems that are used for religion, sports, and advertising, products, restaurants. Um, so you probably recognize a lot of these. And the different types of symmetry are used to create visual designs, visual symbols that represent our logos, our restaurants. So people who make these want to come up with a beautiful symbol, easily recognized and distinct so that as soon as you see the symbol, you know exactly their product, what their product is. So you guys would recognize this probably as Adidas, or some people pronounce it Adidas, but that is our Adidas symbol. Obviously Batman. We have the Star of David. We have the Dallas Cowboys logo, McDonald's, and Starbucks. Each of these pose a different type of symmetry that's used. Now, the reason why symmetry is so important is because our brains, the way they work is we like things in order and neat and symmetric. So it has a certain beauty to it, and it makes us feel more comfortable. When things are not symmetric, it has a tendency to make us feel a little more anxious and like less likely to enjoy that object. So the different types of symmetry used in marketing is so that you see the symbol, know the symbol, and feel comfortable with it and want to go back. So let's just start off with the basics, something simple. Line symmetry. Line symmetry is when a figure can map onto itself. Now, what does it mean to map onto itself? Simply means you can fold it in half. But fold it in half in a way that both halves are the same. And if you fold it in half so both sides line up or match up, fall on top of each other, then you can fold it in half, like your regular piece of paper that you're writing on. You take that piece of paper and fold it, do the hot dog fold or the hamburger fold, you can fold it in half. You can take any generic rectangle and fold it 2 ways and it maps onto itself. The line of symmetry is going to be equal distance, put into one word, equidistant, from all corresponding pairs of points. So I'm going to show you exactly what I mean by that. If I draw a line of symmetry for an isosceles triangle, that's going to be right down the middle through the vertex angle, so that we have the same length leg on each side, and we cut the base perfectly in half. So that means the corresponding pairs of points means this lower left angle perfectly corresponds to this lower right angle, because if I were to take the triangle on the left-hand side and fold it over that line of symmetry, it would fall perfectly on top of the other side. So this corner down here corresponds to this corner over here, because when I fold it in half, they would fall on top of each other. So that's what we mean by the line of symmetry is equidistant from all corresponding pairs of points. If I picked the point in the middle over here, it would perfectly map onto the point in the middle over there. So those are corresponding points. They are both the same distance away from that line of symmetry, from the middle. In an equilateral triangle, we actually have 3 lines of symmetry, one through each side and through each angle. and all three lines of symmetry will meet at one magical point. Now, in an equilateral triangle, this is a very special, unique case because the lines of symmetry bisect the opposite sides, just like in our isosceles triangle, but it also bisects the angle, which also happened over here, but it only did it to one of the angles. In the equilateral triangle, it does it to all three. In a rectangle, there are only two lines of symmetry, which I just mentioned above. You can do the hamburger fold and the hot dog fold. If you pick up your paper right now, your packet, try to connect the opposite angles. If you take that rectangle and try to fold it on the diagonal, does the opposite corner perfectly fall on top of the other opposite corner? Take your paper and try it. It didn't work, right? So the rectangle only has two lines of symmetry, one that goes straight up and down and one that goes sideways. If we have a regular hexagon, remembering that the word regular means all sides are equal, hexagon means 6 sides, we can do a line of symmetry through each opposite pair of vertices and through the middle of each pair of opposite sides. So there are 6 lines of symmetry there. So a line of symmetry is a pretty easy thing to recognize. Can you fold it in half? So some logos that you may recognize that have line symmetry would be the Walmart logo, which if you connected the endpoints, they designed that logo off of a hexagon with a circle around the inside. Or if you connected those inside pieces, it'd be one hexagon inside of another hexagon. So our lines of symmetry would be very similar to what we just did through each vertex and through each bisected side. Our target logo is a circle, so there's an infinite number of lines of symmetry because every diameter would be a line where you could fold the circle in half, so you could keep drawing these closer and closer together to the point where you can't separate the lines. So there's an infinite number of lines of symmetry. The symbol for Chrysler makes motor vehicles is a pentagon. We could do a line of symmetry through each vertex, which would then bisect the opposite side. So there's 5 lines for there. And then BP is a gas station, an oil company. That would be many more lines of symmetry than the Chrysler and Walmart logo, but we could connect point to point. And it is closer to a circle, but technically each one of these would be a straight line, not a perfect curve. But we could draw a line of symmetry through each angle bisector. So that's simple, probably something you recognize, have seen before. What we're going to do next is something a little more complex. And we're going to use this fun childhood toy as a way for us to understand exactly what the next type of symmetry is. So in order to help us understand this next type of symmetry, we're going to watch a short little video. Notice what this child is doing. Matching the blocks with the right shape outline in order to put the shapes into the shape sorter. Trying to figure out which one goes into which hole. You may have had one of these as a kid. You may have seen these babysitting either younger siblings or maybe neighbors or friends. But what we're going to do is use this same concept to introduce something called point symmetry. So here's what I need you to do. I need you to pause the video, and I need you to take these shapes There's one, two, three, four, five, six, seven, 8 shapes that could fit into a shape sorter. And I want you to pretend that you're 18 months old, and I want you to label these shapes 1 through 8 in order from easiest to hardest. So easiest would be number 1, hardest would be number 8. So I want you to just put a number inside each shape. Pause the video, put a number inside each shape, and then what I want you to do is your opinion, so you can't be wrong. Put them in order from 1 to 8, easiest being 1, 8 being the hardest. Which one do you think is easiest for a little kid to find the correct hole? Okay, so pause the video, do that. Okay, so now you have your shapes labeled 1 through 8. Now what I want you to do is pause and go to someone else that's near you, either the person sitting next to you, in front of you, behind you, or wherever, somebody near you, and I want you to compare the order that you picked 1 through 8, your 1 through 8 and their 1 through 8, just to see if you both started on the same one, if you both ended on the same 8. So compare with 1 or 2 people around you just to see who ended up where, then come back to the video. It's important to do this, please. Okay, so when I do this when I'm live and in person, what usually happens, not everybody, the, but a majority of the students in the class will pick the circle as the easiest. And then a lot of them will pick the rectangle as the second easiest because that's the shape that's easily identified. And then from there it goes all over the place. But some people will pick the triangle, the third, the rectangle, and so on and so forth. But I want to focus on 1 and 2. Like I said, I've been doing this for a bunch of years, and most of the time people will come up with number 1 as the circle. And I ask them, why did you pick that as the easiest? And most of them will say, well, because there's a lot of different ways that the circle fits into the circle hole. So you can turn it any way you want. So if I take that circle and spin it, it's still the same shape. So if I take my circle and spin it, it can fit into the circle hole no matter how I turn it. So this circle will fit into this circle hole any way it needs to because it'll fit no matter how I spin it. So I said, okay, that makes a lot of sense. That's probably the easiest one to put into our shape sorter. So then following that logic, and this is where things usually go different from student to student as they go around the room. Following that logic, because this circle can spin any way you want and still fit into the circle hole. Following that logic, what should be number 2 is this one, the hexagon. The reason why that should be number 2 using the same logic as the circle is because the hexagon has 6 different ways that it can turn and still fit into the puzzle hole. There's 3, 4, 5. So there's 6 different ways to fit the hexagon into the hexagon puzzle hole. So that's a lot of options compared to some of these other shapes. Following in the same line of thinking, oops, sorry, excellent explanation, but that should be number 3. Number 2 should be over here. 1, 2, 3, 4, 5, 6, 7, 8. Our octagon should be number 2. Following our logical thinking, that the more ways the shape can fit into the hole, the more success the little child will have. This octagon can map back onto itself 8 different ways until I get back to how I started. So that should be number 2, hexagon number 3, and then following in the same logic around the rest of our shapes, our pentagon would be 4, the square should be 5, the isosceles, I'm sorry, the equilateral triangle should be 6 because that fits 3 different ways. 1, 2, 3. And then the rectangle should be one of the last because that only fits in two different ways. And the very last one is the isosceles right triangle because there's only one way that fits into the puzzle hole, and that has to be perfect and exact. So this is the idea behind point symmetry. The number of ways a shape can be rotated, or the number of ways you can turn a shape, and then it ends up looking the same as how it started. That means it rotates back onto itself. That is what rotational symmetry is. The number of ways a shape can spin or rotate and map onto itself. There's some vocabulary that goes along with this. First word is order. The order is the number of rotated positions in which the object looks exactly the same. That means the number of times it rotates onto itself. The number of times it maps or rotates back onto itself. Now this is the number of times it maps onto itself within one full spin of 360 degrees. So as we were rotating, or as you were watching me rotate this hexagon rotates 1, 2, 3, 4, 5, 6 times back onto itself within one full spin of 360. So that has an order of 6. The octagon here, 1, 2, 3, 4, 5, 6, 7, 8, maps onto itself 8 times, so it has an order of 8. The square would have an order of 4 because it would map back onto itself 4 times within one spin of 360 degrees. 1, 2, 3, 4. So it has an order of 4. Equilateral triangle would be 3, pentagon would be 5. So that's order. If our shape has point symmetry, then we will take 360 degrees and divide it by the order to figure out the smallest angle we need to turn the shape so it maps back onto itself. 360 degrees is one full spin. The order is how many times it maps onto itself. So the number of times it maps onto itself divided into 360 tells us the smallest angle necessary to turn this shape. So for example, we'll go to the square. It's going to be the most obvious one. If I turn the square 4 times, so it maps back onto itself, 360 divided by 4 means every 90 degrees, 90, 90 more, and another 90. Every 90 degrees, it maps back onto itself because it's 360 divided by 4. So the order for rotational symmetry for a square is the number of ways it maps back onto itself. That was 4, 1 for each side. The angle was found by doing a full spin of 360 divided by those 4 positions. Means I have to turn it 90 degrees so that maps back onto itself. To list all the angles, that means I would have to do 90, and then 90 degrees more means I've gone 180 degrees from the very beginning. And then a third 90, 390s is like 9 times 3, 270 degrees, and then we will always end at 360 because that's back to where we started. So there are 4 orders, and each order has a separate angle. 1, 2, 3, 4. Our order of 4, there's an angle for each one. So let's take a look at some of our regular polygons. An equilateral triangle means all 3 sides are the same length. If I were to rotate that, I would have a different angle for each time it maps back onto itself. The equilateral triangle will map onto itself 3 times, so the order is 3. 1, 2, 3. To find the angles that you would have to turn it at, we do 360 degrees for a full turn, divided by it maps onto itself 3 times. So that means every 120 degrees, this triangle ends up mapping back onto itself. So if you did 120 twice, so take 120, add another 120, that means the second angle is 240. Add another 120 to that, and we should always end at 360. If it doesn't end at 360, then it doesn't have rotational symmetry. Our rectangle. How many times does a rectangle map onto itself when you do one full spin of 360 degrees? Well, if I take this rectangle, spin, spin, that's 90, not the same. That's 180. So if I keep going, it only maps back onto itself twice. So if you do 360 divided by 2, then we have to spin it upside down or 180 degrees to get it to map onto itself. And then another 180 gets us back to 360, which is where we should end every time. Our regular pentagon, so long as all sides are the same, 1, 2, 3, 4, 5. Regular means that they're all equal, so it has an order of 5. So 360 divided by 5 would be every 72 degrees. So that is our minimum angle of rotational symmetry. But I should have 5 angles where it maps back onto itself. The first one is 72. Add 72 to that, and we get a second angle of 144. And then what you're going to do is take the current angle measure and keep adding on 72. So 144 plus another 72 makes the next one 216. Then add another 72, which makes it 288. And add another 72, which puts us to 360, which is where we should end up if we're doing everything correctly. And then our hexagon, 6 sides, order of 6, maps onto itself 6 times within one spin. So if we do 360 degrees for a full spin, maps onto itself 6 times, which means it's going to be every 60 degrees. So when I turn this and it maps back onto itself, that means I just turned it 60 degrees. So a second 60 degrees means I've turned it a total of 120 from the original position. And the third 60 degrees means I've turned it 180 compared to its original position. And then another 30, I'm sorry, another 60. Sorry, I accidentally added 30. So this would get us, adding 60 would get us to 240 degrees. Then another 60 would get us to 300. And the last one ends at 360 as it's supposed to. 1, 2, 3, 4, 5, 6 angles of rotational symmetry to match 6 different ways it maps onto itself. So on the test and on your upcoming checkpoint, you may be asked, what's the order? You may be asked, what's the smallest angle of rotational symmetry? Or you may be asked to list all the angles of rotational symmetry. You're just going to have to read carefully to know which to answer. Order, one angle, or all the angles. Rotation of 360 degrees always maps the shape back onto itself. That's called an identity transformation, where it ends up back in the same position as it started. Okay, so that is rotational symmetry. Now we got to get to the more specific point symmetry. Point symmetry is a special case to rotational symmetry. So if you can rotate any angle and it maps back onto itself, that is an angle of rotation. If your list includes 180 degrees, some of them will, some of them won't. If it does include 180, that's when you have point symmetry. So point symmetry means it has 180-degree rotational symmetry. An easier way to visualize is it looks the same upside down. So you could literally turn your paper upside down and see if it looks the same. Are the corners pointing in the correct direction? So if I trace this parallelogram, and then I can take it and spin it 180 degrees, you can see that it maps back onto itself. So that has point symmetry because it looks the same upside down. If I do the same thing with this flag type looking shape, I can trace it, rotate it 180 degrees, and it maps back onto itself. So it looks the same upside down. If you try to do that with a triangle, it is not going to work because a triangle has an odd number of sides. Any shape with an odd number of sides will not look the same upside down. The points are in the wrong place. So that's why it does not have point symmetry. Not everything that has an even number of sides will have point symmetry. It has to look the same upside down. So this isosceles trapezoid, you can draw a line down the middle, but it doesn't look the same upside down. So that's the idea behind point symmetry. It has to look the same upside down. So the third part to this is total number of symmetries. And the word total means add everything together. So we just talked about lines of symmetry at the very beginning. So we can draw a line down the middle or fold the shape in half. We talked about rotational symmetries. How many times will it spin and land back on itself? So total symmetries is when we add them together. So our equilateral triangle had 3 lines of symmetry, and it had an order of 3, so it had 3 angles of rotational symmetry. So according to childhood math, 3 lines and 3 angles make a total of 6 rotational symmetries, 6 total symmetries. Okay? So let's just make sure we understand this. Which of these shapes look the same upside down? And which of these letters look the same upside down? So pause the video, take whatever time you need, and figure out which shapes look the same upside down and which letters look the same upside down. When you're done picking those out, then you can come back. So this first one, let's just take a look. If I turn it upside down, look at that, maps back onto itself. So this does have point symmetry. This one is a yes. Any shape that has an odd number of sides when turned upside down will have the points in the wrong place. So this one is a no. If you're not sure, we can take the shape, spin it upside down, see if it maps onto itself, and that one does. You can also just take your paper and literally turn your paper upside down and see if it looks exactly the same. The reason why decks of cards are designed the way they are is so that they look the same upside down. You can tell that I spun this upside down, and it looks the same as the original. That way, when you're holding the cards in your hand, it doesn't matter which side's up. This is a symbol for Hyundai cars. And if I spin this upside down and compare it to the original, it is not exactly the same. And then another car logo. If I spin this upside down, that one is the same. So let's check our capital letters of the alphabet. If I take the letter A, spin it upside down, it does not look the same. You can just take your paper and turn your paper upside down and make sure the letters are facing the same order. The letter E, not the same. With the letter H, will take the letter H, spin it upside down, still looks like an H. Same thing will happen with the letter N and the letter S and the letter X. Here's the letter N, upside down, still an N. Letter S, upside down, still an S. The letter X, upside down, still an X. But the W, when turned upside down, you can probably imagine this, or already knew this, changes letters to an M. Okay, so now we can apply some of our construction techniques because we just finished our construction unit on Friday. If we wanted to construct one line of symmetry, and this is a pentagon with an odd number of sides, that means we have to do an angle bisector construction, which I'm running out of time. An angle bisector construction, oops, that was ugly. We'll bisect the angle to make it go right down the middle, and bisect the opposite side. So you're supposed to use a compass and a straight edge to bisect that. When you do that to two angles so that it bisects the sides, you can find the center of rotational symmetry. So the center of rotational symmetry has to be the point exactly in the middle where all the lines of symmetry meet. So there is line symmetry, there is rotational symmetry, but it does not look the same upside down, so there is no point symmetry. This has 5 sides, so the order is 5. So it has 5 rotations where it maps onto itself. Each one comes after a 72-degree turn. And we listed these out earlier in the notes. That's how I'm going through these so quickly. And there are 5 lines of reflection. So on the next page, total symmetries, 5 rotations plus 5 lines equals a total of 10. All right, y'all, go to your homework or go to your weekly and do some practice. And I will see you soon, and we can go through any questions that you may have. Be nice to each other, and take care.